Continuation of the last week's one, and it's titled Geological and Geochemical Studies of Halifax Harbour. Once again, the head of that study is Dr. Dale Buckley of Bedford Institute of Oceanography. By education, he has a bachelor's from Acadia in geology, a master's from the University of Western Ontario in geochemistry, a pre-doctorate degree from University of Southern California in colloidal chemistry and marine geology, and a doctorate degree from University of Alaska in marine sciences. And he's a specialist in the geochemistry of sediments and water. And he has been with the BIO ever since its inception, I think.
That's right.
In 1962. And he has been conducting very advanced acid-based research. And he's a research scientist in geochemistry and sedimentology. And he's the one who discovered some very, very major aspects of the Halifax Harbour, which created quite a bit of stir in the scientific community, as well as actually indirectly, partly was responsible for the Premier's creation of the Dr. Fournier Task Force on Halifax Harbour. So, Dr. Buckley, if you can give a short introduction for people who didn't switch on the last show, and then continue the lecture format.
Sure. Well, in the previous program, I reviewed some of the work that we have been doing for the last 2 years on Halifax Harbour, based mainly on sampling of bottom sediments throughout the harbour, and showed something about how you could actually see a difference in the sediments because of their very black nature when they are deprived of oxygen, and the fact that when you go offshore you can see more reddish colored sediments in the surface, which is an indication that the sediments have been exposed to oxygen. And now we are moving into some of the analytical results that we have obtained from a chemical analysis of the sediments, and are beginning to look at how we can interpret this data. The illustration here is the map of the distribution of copper in the sediments. Now, copper is used as a diagnostic element to show the effects of man's influence on the environment. And Halifax Harbour has several very obvious points that show the effect of the discharge of sewers. Mainly, these can be seen just off the town of Bedford, where there is a very obvious anomaly of copper in the sediments. There are two very bright spots in Bedford Basin, one in almost the north-central part of it, and another one in Wright's Cove. The one in the north-central part is in fairly deep water and is a bit of a mystery, or at least it was, until a few days ago when we saw a map which showed that this is almost directly on top of an area that was used by D&D for a disposal site back in the Second World War. So our samples were obviously picking up something that had been dispersed in the sediments. The Wright's Cove area is obviously coming under some kind of stress from contaminants that either are being discharged from sewers or natural seepage in that area. There's another less intense anomaly off of Seaview Point, and that's an area that used to be the municipal landfill site. And so some of the material is actually leaching out of that landfill site into the Bedford Basin. You can see three bright spots down through the narrow section of the harbour. One is a combination of the effect from the Tufts Cove outfalls and the Duffer Street outfalls. Another one is along by the Halifax-Dartmouth shipyards, and then another very bright one off of CFP Halifax. There are a number of sewers, of course, that enter into the harbour in that area. There are 40-some altogether along both the Halifax and Dartmouth waterfront areas, but there are some major ones, and that's showing up quite obviously in the data that we have here. Over on the Dartmouth Cove side, you can see that there's a very small but intense anomaly of copper coming from the center of Dartmouth Cove. On the Halifax side, the Pier A outfall is very obvious again, and an interesting point here is that the dispersion of the copper in the sediments is going inward in the harbour. and curling around the north end of George's Island. That's a very instructive point because it tells us something about where the sewers, the outfall material is going from the sewers. And instead of it going offshore, it is apparently being dispersed inward in the harbor. You can see that most of the northwest arm has a high concentration of copper in the sediments. But a very interesting point here is that very little of this copper, in spite of the fact that there are samples at some points that are up as high as 1,500 parts per million, which is an extremely high copper content. Those high contents are not getting offshore. They're not getting out past basically the cross-section between McNabb's Island and Sandwich Point. Now, a number of the other elements show somewhat a similar pattern. This is lead, which is a very diagnostic type of contaminant. And you can see that the anomaly that we saw in the copper in the middle of Bedford Basin shows up again. That would make one suspicious that it might be something from the disposal, perhaps of something like wet cell batteries that is that's releasing some of the material into the sediments. That would also be a suspicion that it's material, something like that, that's coming from the Seaview Point landfill site, because there's very obvious anomaly of lead right off of the tip of Seaview Point. There are also lead anomalies at CFB Halifax and at the Dartmouth Cove, at the Pier A site, and more or less throughout Northwest Arm. Now, lead is one common source of lead is from the use of lead-based paints. And they reached their peak in common use in marine paints, that is, at least, in about the late 60s. So most of the lead that we see in these sediments may be related to that source, but there are many other sources that could be contributing to that contamination. Again, you can see that very little of the lead is getting in the sediments that go out past McNabb's Island. So most of it's being retained within the harbor system. And this is a metal, mercury, which is a very obvious environmental concern because of its association with Minamata disease. That is a disease that was identified in Japan and was a lethal disease when Japanese people ate fish that was contaminated with mercury. So that's focused much attention on this metal because it is a highly toxic metal. Mercury is unfortunately a common ingredient in sewage. And so it shows up here very obviously coming from most of the points that we have mentioned before. Bedford, the town of Bedford obviously is releasing some mercury in the sewage sludge that comes out through Mill Cove. There is a very large anomaly near the Bedford Institute of Oceanography. We suspect that that material is actually material that was released in the outfalls from Tufts Cove and Duffer Street and is being swept through the narrow section by the tidal currents. And remember, in one of the previous illustrations indicated that the direction of the dispersion appears to be inward in the harbor, along the bottom in particular. So it may be that some of the mercury-rich sludge that comes out of the Duffer Street outfall and perhaps the Tufts Cove outfalls is actually being carried into Bedford Basin. And it would be logical for it to be deposited on the northeast side of the Bedford Basin, because that would be the direction in which the bottom currents might be deflected once they have come through the narrows.
Dr. Buckley, where does the mercury come in sanitary sewage from?
Well, there's a lot of sources of mercury. Mercury was commonly used in paints as an antifungicide. Even latex paints that were used in households used to contain a lot of mercury. Mercury is a common ingredient in pharmaceuticals, in a lot of the makeup material that is used. Mercury is a common ingredient. One of the most common and likely sources is probably the bleaches that we use in households. They are made by a process which inadvertently adds mercury to the bleaches. So that is a suspicion that that's a common association.
Oh, you mean bleach for the unbleachables? That kind
Yes.
They have mercury in them?
Yes. Yeah.
Oh, I'll have to stop using them.
In the past, of course, this was a much greater problem than it is today, because the process of making and manufacturing chlorinated compounds required a mercury electrode system, and so there was some mercury inadvertently released into the product, which then got used in the environment.
Before you go to the next slide, is there a way to remove mercury from?
Yes, it is, but it's a very expensive process. Now, it has been required that it be removed, or at least reduced, in the case of the chloralkali plants that produce salt cake, for instance, for the pulp and paper mills. Back about 15 to 18 years ago, there were regulations that required them to remove the mercury from that salt cake. And so as a result of that, there has been a very good improvement in the quality of effluents around pulp mills and so on. Well, this distribution of mercury is quite instructive in Halifax Harbour. Again, you can see that the areas in Dartmouth Cove and in the Pier A area, the dispersion of the plumes from that goes inward in the harbour, and that very little of the mercury appears to be getting out of the sediments in the northwest arm. Now we'll take a look at another dimension of the contamination in the sediments. So far, we've only been looking at the 1 centimeter thick layer of surface sediments throughout the harbour. We have a series of cores that were taken at several points, and I'm going to go back to an illustration. If we look at this chart and remember the bright red dot that was in the middle of Bedford Basin, more or less the north-central part of Bedford Basin, and move slightly towards the town of Bedford, one of our cores is located there. So it's in quite deep water, still in Bedford Basin, but not in the center of Bedford Basin. Then the second core that I'll show the results from is located just to the north of George's Island, so it's in the Halifax Harbour proper. And the third core is in the northwest arm, fairly near the dingle. So this represents 3 sort of major subdivisions of the harbour system. And these profiles here are the plot of the concentration of copper. And actually I've shown 2 different ways in which that data was obtained. The profile slightly on the left of each of the cores is the concentration of copper that's associated with organic material. And the profile on the right of each of the cores, the red color, if you have color, shows the total concentration of copper. That's quite instructive because it tells us that almost all of the copper is being tied up with the organic material in the sediments. The other feature which is very interesting and very instructive is to show that in the deeper parts of these cores, the concentrations fall to quite low levels. If you look at the core number 1 on the left-hand side, you'll see that the concentration of copper below 30 centimeters depth is quite constant at about 10 parts per million. And that's quite a low concentration. But then it begins to increase as you go towards the top of the core, increasing up to about 50 or 60 parts per million. In the core number 16, you can see that concentration begins to increase at about 45 centimeters, goes up to a concentration of around 130 at the maximum, and then decreases slightly towards the top. And the core 24, now core 24 is located in the northwest arm, and again it increases quite dramatically from about 25 or about 15 centimeters up to near the surface and then decreases again. There's a bit of detective work that has to be done here, and one of the things that we need to know is what is the date at which that material begins to increase. In the case of core 1, we have quite a strong suspicion that 30 centimeter depth represents about 1900, and that the increases go up to a maximum around 1965 or so, and then there's a disruption in the profile with a sharp decrease and then an increase again. In core 16, which is just north of George's Island, the peak values in copper are occurring at around 10 centimeters. That's, we think, is around 1968, and then a fall off towards the top. Again, the same thing is shown in core 24. So copper is very clearly related to man's activity, and it looks like the significant increases began around 1900. If we look at lead, this is very instructive from a couple of points of view. First of all, if you look at the results in all the cores, the blue profile, that is the little profile on the left of each core, shows that there is very little of the lead that is associated with the organic material in the sediments. Almost all of the lead is what we would call inorganic lead. That is, that it's tied up in some phase that is not related to the organic matter. Again, it shows much the same thing as copper, with a very sharp increase from what we think is around 1900 up to a peak around 1968, 1965, somewhere in the mid to late 60s. If you remember a little while ago, I mentioned that lead was very commonly used in lead-based paints, especially in marine applications above the waterline. And then it decreased very sharply after that. In other words, it was not sold basically after about 1971. And so what we might be seeing here is the effect of decreasing use of lead in marine paints. Now, obviously, some vessels that were painted before 1970 perhaps were not scraped or maintained until later, so there would still be a release of some of that material going into the sediments. So we may be looking at a man's use of lead in paints, primarily here with the lead-based paints. Mercury follows a very similar profile to lead, and that makes us suspicious that perhaps mercury is primarily coming from paints. However, there are some quite unique differences too. In core number 1, for instance, the increase in mercury doesn't begin until quite a bit later than it did with lead. And the peak is very much sharper in the core number 16, which is located north of George's Island. In the case of core 24, the lead and mercury profiles are almost identical. So there seems to be a relationship between the input of mercury and the input of lead. Now, this is a fascinating part of our research, because if we can find out when these contaminants came in and when they started to increase in concentration, it gives us some way of measuring the impact of the sewage disposal and solid waste disposal on a harbor system. It also tells us something about which kinds of waste disposals are likely to be the most hazardous, because if we can tie up that it is in fact coming from paints, or if it's coming from some chemical we're using, then we can get some way of managing that problem. Well, that essentially finishes the lecture part of my talk, in which we present some of the data that we're working on at the present time.
I was wondering when the decision will be made with respect to the treatment plants, would they be, do you think, would they be considering removing these things like mercury and lead? Or,
well, that's something which...
That's pretty advanced treatment, I think.
That would require a very advanced treatment. That's something which I would not particularly have an expertise in as to what kinds of treatments would be required to remove things like this. We do know that primary treatment removes about 50% of the particulate load that goes in from the sewage. And since many of these contaminants are carried on particulates, then that is an advantage to get out as much of the particulate as you can. But I mentioned in some cases metals like copper are very strongly associated with the organics. So one of the things you would be concerned about is that you reduce the organic inputs.
Well, that would mean something like an advanced secondary treatment, I would say.
Yes, it depends. There are so many different grades of treatments now, going from, there are several different grades of primary treatment. There are advanced primary treatment, secondary treatment, advanced secondary treatment, and so on. So there are, almost every plant is unique in what its capability is.
So what were they originally planning, what kind of a treatment were they using at one time?
Well, I'm afraid you'd have to ask somebody else that.
No, I mean, I know the plan is canceled for the time being until this Fournier task force comes up with this. The next thing I wanted to ask, this is just my opinion based on, non-research opinion, plus I've attended a lot of meetings. It looks like, it's, as I say, it's my opinion, and it was a bloody mistake whoever made this decision, I guess the Metro Authority, to go and dump the things in Sandwich Point, Herring Cove, without kind of a detailed study that BIO is doing?
Well, certainly I think much of the data that we're collecting now will be a good foundation on which to base any kind of decision. There were certainly things that have come from the work that I've been doing as well as other of my colleagues that I think will help the planning process. Things like knowing the type of sediments that are on the bottom at the present time, even knowing something about where there are sand deposits and where there are mud deposits and so on is sort of vital information when one is talking about location of outfall pipes.
Such a major thing, a $200 million project.
Sure.
Again, I give my own personal opinion. It looks like the best treatment option is one treatment plant in Dartmouth and one in Halifax.
Well, again, I think there's a lot that goes
I've
into
already
that.
made my conclusion before the 4-year task force comes up. It's free for all of your listeners.
I think some of the things that go beyond the aspects that I've been talking about is also the physical oceanographic studies will have a very important component in that decision as to where treatment plants might be located or where outfalls may be located. So it's not just simply the results of one discipline study. It has to be.
Who is heading that?
Well, there are a number of people that have been involved in it. There have been contract studies done to collect the data, and some of the data is being interpreted at the Bedford Institute of Oceanography.
Who's the head of that study?
Well, it's a group, essentially, and it's a physical oceanography group that's involved in parts of that study. And there's a contractor that is also involved in the modeling studies with the interpretation of the data.
I see. Then my next thing is that we've always been interested in the Sackville River, as you know, through the media and everything. And I'm also the chairman of Sackville River's Advisory Board. Just one of my numerous activities. And I'm really surprised that at one time the river was a mighty river. You were saying that Bedford Basin was a lake one time?
Yes, that's right. Yes.
And how did you people prove that?
Well,
it's
we
just
can tell
fascinating,
one of the things that I didn't show here tonight, but we have some long cores. The data I was showing tonight were from short cores. We have one particular long core that actually goes through the surface sediments and down to 10 meters depth in the sediments. And the animals that lived at that time are freshwater species. We also find ones that are marginal, that is, that they were living in a marshy kind of environment. And as you go up in the core, you find that they become progressively more salty. So there's everything from a lake environment to a marsh environment up through to present-day marine estuarine environment.
I see. So the lake turned into a marsh, right? And then turned into marine?
Yes.
What?
Yeah.
I thought, I see.
Because it would have been different stands of sea level. 6,000 years ago and earlier, the sea level would have been much lower than it is now.
I see.
The relative sea level, because both the land and the absolute level of the sea have changed. So when the sea level was approximately 20 meters lower than it is today, there would have been a sill across, essentially, where the Narrows is. So seawater could not have gotten into Bedford Basin. Only fresh water could have gotten out through the Sackville River system.
I see. That's very, very interesting. This kind of makes me believe that we should increase, I'm just talking in general, that we should increase the level of research in our country, Canada, because many times I think we make decisions based on archaic technological systems, because I'm in technical related fields myself. And I think we too often are in a hurry to make decisions without, let's say, fundamental research, like physics and geology and microbiology, the whole thing, especially in major projects.
Well, I'm glad to hear that, because I think...
no, I'm a strong supporter of science myself, and actually about 70% of my family are all scientists, both among my family and my relatives. And sometimes you feel, like the average Joe usually feels that, what is the purpose of all this when it's too theoretical? But it does lead to final solutions. It's like research in medicine,
Sure. It's applied science.
Like you can't just make discoveries overnight. First you have to work with fundamental fields and then apply. And this BIO is one of the top ones in the world.
Well, in terms of size, at one time the Bedford Institute was probably the second or third largest institute in the world. And in certain terms of, I suppose, influence in whatever way you want to measure it in terms of scientific publications and so on, it's certainly one of the very top institutes in the world.
It still is?
Oh, yes.
What about in Canada?
Oh, it's the largest by far in Canada. At one time, of course, it was the only national oceanographic institute. There are several departments of oceanography or marine studies at universities, but now there are other centers of federal government research in oceanography now, at Sydney and British Columbia, and at
Sydney?
Yes, on Vancouver Island. That's essentially the West Coast equivalent of the Bedford Institute of Oceanography, but it's a smaller institute. And the Maurice Lamontagne Institute in Quebec is a new institute, which is also a federal institute.
BIO represents 3 different disciplines, doesn't it?
Well, more than 3 disciplines. It represents 3 departments. Department of the Environment is fairly small, located at...
You mean Environment Canada?
Yes. And the Department of Fisheries and Oceans is by far the largest, and the department that I work for is the Department of Energy, Mines and Resources. There are all kinds of specializations, everything from hydrography, mapping programs, to engineering, biology, chemistry, geology, geophysics. So there's a great variety of sciences that are being conducted there.
Dr. Buckley, I was thinking, how did you start this project in Halifax Harbour? Was it part of a research project, or was it required by somebody?
For the past 10 years, prior to 1988, I had been working in the deep sea on the radioactive waste disposal program. And we had made a number of discoveries about the geochemical behavior of deep sea sediments. And I wanted to test some of the theories that we had developed from the deep sea on nearshore materials. And I wanted to pick an area where we knew that there was a very strong chemical gradient, and Bedford Basin was an ideal site.
I see.
So that's how we actually began our studies, and then through some inquiries from the Department of the Environment, they asked us if we would do superficial sediments sampling and analysis, which we did, and that kind of led us into the studies in the harbour.
I know the Premier of Nova Scotia, I mean, the official representative of the people, he respects BIO statements, because if you remember, last year he said when people from Herring Coal complained, usually people complain anyway, like the NIMBY syndrome, he said when BIO scientists say something, he'll listen, he said. So
that was a very nice
So
compliment.
that gives it credibility,
Yes, sure.
And I congratulate all of you scientists, because almost all of us are environmentalists now, whether we admit or not, because we know we want to live in clean lives and other things. So I thank you very much for having graced our show, Dr. Buckley. And thank you, audience.
Thank you.